25,900,000,000 kilometers? That is not a rounded guess. That is roughly where Voyager 1 sits right now, a single human-made object drifting through a region of space so remote that a radio signal traveling at the speed of light needs almost 23 hours just to reach it, and another 23 hours to get an answer back. 46 hours, round trip, for a hello and a yes, I'm still here. The spacecraft carries a computer with less processing power than the key fob that unlocks your car, running code written by engineers who assumed it would be silent by 1980. It has been running for 48 years. And a few years ago, without moving an inch off its outbound path, without turning around, without doing anything except quietly listening, Voyager 1 sent home a signal that made scientists stop, stare at a plot on a screen, and ask themselves if they were seeing things. They were not seeing things. What that faint signal revealed about the space just outside our solar system was real, it was measured, it was published, and it answered a question humanity has been almost afraid to ask out loud. What is actually out there once you leave the safety of the sun's bubble? The answer is not a monster. It is something quieter and in some ways stranger, and it forces us to reconsider exactly how alone, how exposed, and how small our little corner of the galaxy really is. To understand why that faint signal mattered so much, you have to go back to where this whole journey started, because Voyager 1 was never supposed to become humanity's first interstellar explorer. It was built to be a planetary tourist. In the summer of 1977, NASA launched two nearly identical spacecraft within weeks of each other, taking advantage of a planetary alignment that happens roughly once every 176 years, where Jupiter, Saturn, Uranus, and Neptune line up in a way that lets a spacecraft slingshot from one to the next using gravity instead of fuel. Voyager 2 launched first, on a slower path, built to eventually reach all four giant planets. Voyager 1 launched 16 days later on a faster trajectory, aimed squarely at Jupiter and Saturn, sacrificing the outer planets for speed and for one specific, deliberate encounter with Saturn's largest moon, Titan, a place scientists suspected might hide something like an atmosphere thick enough to matter. Both spacecraft carried something that had nothing to do with science instruments at all. Bolted to the side of each probe is a gold-plated copper phonograph record, sealed in an aluminum jacket, engraved with symbolic instructions for how to play it, in case anything or anyone ever finds it. Carl Sagan led the committee that assembled it. On it, greetings in 55 languages, the sound of wind, rain, and surf, a baby's first cry, whale songs, Bach, Beethoven, Chuck Berry's Johnny B. Goode, and 115 images encoded in analog form showing our anatomy, our cities, our food, our diagrams of DNA and mathematics. It is, quite literally, a message in a bottle thrown into the ocean of the galaxy. Except the ocean is so vast that even traveling at over 61,000 kilometers per hour, Voyager 1 will not come within a few light years of another star system for roughly 40,000 years. The record was never really meant to be found. It was meant to say something about us, to us, at the moment we first admitted how small we are. The spacecraft's actual mission, the one it was funded and engineered for, took just under 3 years to complete. Voyager 1 reached Jupiter in March of 1979 and returned images that rewrote textbooks overnight, discovering active volcanoes erupting on the moon Io, the first confirmed volcanic activity found anywhere in the solar system besides Earth, and revealing faint rings around Jupiter that no one had confirmed existed before. It reached Saturn in November of 1980, delivered stunning imagery of the ring system's fine structure, and then did the thing it had been sent to do above all else. It flew close past Titan, close enough to determine that the moon was wrapped in a dense nitrogen atmosphere thicker than Earth's own, a discovery so significant it justified bending the spacecraft's trajectory up and out of the plane of the solar system, permanently ending any possibility of visiting Uranus or Neptune. Voyager 2 would go on to be the only spacecraft in history to fly past all four gas giants. Voyager 1 gave that up for one moon because that one moon mattered more. And then it just kept going. Outward, away from the sun, past the orbit of Pluto, into a region scientists call the heliosphere, the outer edge of the bubble the sun carves out of interstellar space with its solar wind. In February of 1990, at the request of Carl Sagan, mission controllers turned Voyager 1's camera around one last time and had it take a series of images looking back at the inner solar system before the camera was powered down for good to save energy. In one of those frames, Earth appears as a single pixel, less than the size of a period at the end of a sentence, suspended in a scattered ray of sunlight. Sagan later described it as a pale blue dot, and wrote that everyone who has ever lived, every triumph and tragedy in human history, happened on that speck of dust hanging in a sunbeam. That photograph is, to this day, one of the most quietly devastating images ever produced by a scientific instrument. After that, the cameras went dark permanently. There was nothing left to see in visible light worth the power it cost to look. For the next 22 years, Voyager 1 traveled through a kind of no man's land, The outer heliosphere, where the solar wind, the stream of charged particles constantly blown outward by the sun, begins to slow down and pile up against the pressure of the interstellar medium pushing back from outside. Think of it like a ship's bow wave. The sun is not sitting still in the galaxy. It is moving through the interstellar medium at roughly 23 kilometers per second, and that motion, combined with the outward pressure of the solar wind, inflates a vast bubble around the entire solar system called the heliosphere, somewhere out past 100 astronomical units, an astronomical unit being the distance from Earth to the sun, roughly 150 million kilometers. That bubble finally runs out of pressure and the interstellar medium takes over. The boundary where that handoff happens is called the heliopause, and reaching it, confirming it, measuring it, was one of the last great open questions in solar system science, because no human-made object had ever gotten there before, and nobody actually knew for certain when Voyager 1 would cross it, or even how you would prove that it had. The proof came in stages, and it came from data, not guesswork. In 2004, Voyager 1 detected a sharp jump in the strength of the magnetic field and a slowdown in the solar wind, signs that it had crossed something called the termination shock, the point where the solar wind abruptly slows from supersonic to subsonic speeds as it starts running into the pushback of interstellar space. That put it in the heliosheath, the turbulent transition zone, but not yet outside the bubble entirely. It would take another 8 years of travel through that zone before the real crossing happened. On April 9th, 2013, mission scientists announced something remarkable, based on data that had actually been recorded back in 2012. Voyager 1's plasma wave instrument, an instrument originally built to study the solar wind, had picked up locally generated electron oscillations, vibrating at a frequency of about 6 kilohertz. That frequency corresponds directly to an electron density of about 0.08 particles per cubic centimeter. That number matters enormously because inside the heliosphere, plasma density hovers around 0 to 0.2 particles per cubic centimeter, 40 times lower. Crossing into a region where the density jumped by that much was essentially a smoking gun. Voyager 1 was no longer swimming in solar wind. It was swimming in the material between the stars. NASA dated the actual crossing to August 25th, 2012, meaning Voyager 1 became the first spacecraft in human history to leave the heliosphere and enter true interstellar space, 35 years after it launched, at a distance of about 121 astronomical units from the sun. That should have been the headline discovery, and for a while it was. But it also created a new problem, a much stranger one, because now scientists had a spacecraft sitting in genuinely unexplored territory with instruments that were never designed for the job. Voyager 1's actual plasma instrument, the one meant to directly measure the density and speed of charged particles by sampling them, had failed decades earlier, back when the spacecraft was only about 10 astronomical units from the sun. So once Voyager 1 crossed the heliopause, scientists lost their most direct way of measuring the density of the interstellar medium around it. They were flying blind through the exact region they most needed to understand. The only tool they had left was the plasma wave instrument, and that instrument could only detect density indirectly, and only when something disturbed the plasma enough to make it oscillate, like a solar eruption traveling outward from the sun and slamming into the interstellar medium months or years later, producing a burst of oscillations Voyager 1 happened to be positioned to hear. Those events were rare. Sometimes years passed between them. It meant scientists had, at best, a handful of isolated snapshots of the density of interstellar space, separated by long, silent gaps where they had no idea what was happening in between. And that brings us back to that moment, sometime around 2017, when a graduate student, staring at a plot of Voyager 1 data, noticed something that should not have been there. Not a burst, not a shockwave event. A faint, narrow, almost impossibly weak signal, so quiet it barely rose above the instrument's own noise floor, but persistent, showing up again and again, continuously, in a way no one had predicted and no theoretical model had called for. It took years of careful analysis to confirm what it actually was. A continuous hum of plasma oscillations coming from the interstellar medium itself, not triggered by any solar event at all. Just the ambient background noise of the space between the stars, ringing at a frequency that could be converted directly into electron density. For the first time, scientists had a way to measure the density of interstellar space continuously, sampled every few weeks instead of once every few years, filling in a map of the region that had previously been almost entirely blank. What that continuous hum revealed, once researchers had years of it stacked together, was published as one of the more quietly unsettling results to come out of the Voyager program in the past decade. The density of the interstellar medium is not smooth. It is not calm. It fluctuates on scales of roughly 1 astronomical unit, the same rough scale as the distance between Earth and the Sun, rising and falling in ways that trace out turbulence, actual physical churn and structure in the material between the stars, the kind of turbulence long theorized to come from either distant, ancient supernova explosions still rippling outward across the galaxy, or from more local disturbances generated where the heliosphere itself grinds up against the interstellar medium. In other words, the space just outside our solar system, the space that surrounds essentially all of known human history and civilization on a truly local galactic scale, is not empty and it is not still. It is turbulent. It has weather of a kind, texture of a kind, structure that ripples and shifts on timescales and length scales that are, frankly, alien to how most people picture empty space. Then the data kept coming because Voyager 1 kept moving, and by the early 2020s, researchers had tracked something even more specific. Right around 2013, when Voyager 1 first crossed into interstellar space, the electron density it measured was consistent with roughly 0, 0.8 particles per cubic centimeter. But as the spacecraft continued outward, that density did not stay flat. It rose, and rose sharply, by a factor of roughly 40, reaching its higher, steadier level by around the middle of 2015, and then, remarkably, holding in that elevated range with fluctuations for years afterward, all the way out past 160 astronomical units. A pressure pulse detected around 2020 at roughly 149 astronomical units from the Sun seemed to mark another turning point, after which the density measured by Voyager 1 settled into a new plateau, sitting around 0. 147 particles per cubic centimeter based on the most recent readings, a level scientists now believe may represent something close to a broad density peak, a genuinely new physical regime out there rather than a temporary fluctuation. Why does any of that matter to someone who is never going to read a plasma physics journal? Because it directly undermines a comforting assumption a lot of people quietly hold, the assumption that our solar system sits inside some kind of stable, symmetric, well-behaved bubble, gently floating through calm, uniform, empty interstellar space, like a soap bubble drifting through still air. That is not what the data shows. It shows a heliosphere that is being actively compressed, shaped, and pressured by an interstellar medium that has its own internal structure, its own density gradients, its own turbulence, a medium the Sun is plowing through rather than floating in. Some researchers now describe the outer boundary region the spacecraft is passing through, the outer heliosheath, as a zone where the interstellar plasma flow itself gets significantly decelerated and heated by the collision with our solar system's own outward pressure, a genuine, ongoing physical interaction between two systems, not a clean, silent handoff at a fixed boundary line. And models suggest the density of both plasma and neutral atoms out there may keep climbing until the spacecraft, and by extension, our understanding of this region reaches somewhere around 200 to 250 astronomical units from the Sun, a distance Voyager 1, moving outward at its current pace, would not reach for a very long time. There is something almost uncomfortable about sitting with that fact. For virtually all of human history, space meant the sky above us, the moon, the planets, maybe the stars as fixed points of light. Only in the last 100 years or so did we really grasp the scale of the galaxy, and only in the last 50 have we had a single physical object far enough away to actually measure directly what the space between star systems is like, rather than infer it from light passing through it from somewhere else. And what that one object found is that the boundary of our home is not a wall. It is a battlefield, a zone of pressure and pushback and turbulence, shaped by forces from both inside and outside our solar system, some of them possibly originating from stellar explosions that happened before humans existed, whose shockwaves are still rippling through the galaxy and washing up against the edge of our own cosmic backyard. We are not floating serenely through the void. We are being pushed on, constantly, by a much larger and much less orderly galactic environment than most of us ever imagine. None of this is really a story about danger in any immediate sense. Nothing about a slightly elevated plasma density 40 billion kilometers away threatens anyone on Earth. But there is a different kind of unease buried in it, a philosophical one rather than a physical one. It confirms something people have quietly suspected, but rarely had direct evidence for, that once you leave the shelter of the Sun's influence, the universe does not become calmer, cleaner, more orderly. It becomes rougher, less predictable, full of structure and motion we cannot see with our eyes, and could not have anticipated without an instrument, almost by accident, catching a signal so faint that a scientist genuinely wondered if she was imagining it. We built one machine, sent it out on a fluke of planetary alignment nearly 50 years ago, and it is still, today, teaching us that the picture of interstellar space in most people's heads, empty, silent, still is simply wrong. There's also a harder, more immediate kind of fear buried in this story, one that has nothing to do with plasma physics and everything to do with time. Voyager 1 runs on plutonium. Specifically, it carries 3 radioisotope thermoelectric generators, devices that convert the heat given off by the natural radioactive decay of plutonium-238 into electricity. There are no solar panels. At this distance, the sun is far too dim to power anything, appearing as little more than an unusually bright star. The plutonium decays at a fixed, unstoppable, entirely predictable rate, losing about 4 watts of power output every single year. A slow and silent countdown that has been running since before the spacecraft even left Earth. In the early years of the mission, there was more than enough power to run every instrument at once. That has not been true for a long time. Engineers have been shutting instruments off one by one, permanently, for over a decade now. A rolling, irreversible triage list, prioritizing whichever instruments still return the most scientifically valuable data per watt of power spent. The infrared instrument was shut down decades ago, after the planetary flybys ended, since there was nothing left in its field of view worth studying. The cameras went dark after the pale blue dot photograph. In more recent years, engineers have had to shut off heaters protecting instruments from the extreme cold of deep space, gambling, correctly so far, that decades-old hardware would keep functioning even after losing its thermal protection because there was simply no other way to keep the mission alive without freeing up power somewhere. The plasma wave instrument, the one responsible for the discovery of that continuous interstellar hum, the one currently rewriting our understanding of the space just past the edge of the solar system, is one of the instruments still running. But it will not run forever. Every projection from mission engineers points to the same grim arithmetic. Somewhere in the back half of this decade, the declining power output will fall below the threshold needed to keep even a single scientific instrument operating. And at that point, Voyager 1 will still exist, still be transmitting a faint carrier signal home, but it will effectively go silent as a scientific instrument for good. The spacecraft itself, the hardware, will likely keep drifting for millions, maybe billions of years, essentially forever on any human timescale. A genuinely permanent artifact of our civilization, outlasting every pyramid, every monument, every structure ever built on Earth. But the science, the discoveries, the ongoing conversation between this one small machine and the scientists on the other end of a 46-hour round-trip radio link that has a hard, foreseeable, approaching expiration date. We are, right now, in the final years of ever getting new information from the only object humanity has ever sent far enough to directly sample the space between the stars. That is the quiet, uncomfortable truth sitting underneath this whole story. We spent decades building the picture of interstellar space that Voyager 1 is currently overturning, and we are going to lose our only direct source of new data on it at almost exactly the same moment we are starting to understand how much more complicated and dynamic that environment actually is. There is no planned successor. No spacecraft currently under construction is designed to reach interstellar space and keep functioning once it gets there. The distances and timescales involved make it an extraordinarily difficult and expensive, decades-long undertaking, and nothing like it exists in any near-term mission roadmap. When Voyager 1 finally falls silent, humanity will, for the foreseeable future, go back to inferring what interstellar space is like from a distance, the way we did before 2012, rather than measuring it directly. The window we have had, this narrow, improbable, almost accidental window where a 50-year-old spacecraft with a stroke of engineering luck happened to keep a single sensitive instrument alive long enough to catch a signal nobody designed it to detect, is closing. And yet, framed a certain way, that is not really a story about fear at all. It is a story about how much can be learned from paying close attention for a very long time with instruments that were never designed for the job they ended up doing. Nobody who built Voyager 1's plasma wave instrument in the 1970s imagined it would spend the 2020s mapping turbulence in interstellar plasma. It was built to study the solar wind near the giant planets, a completely different scientific target, on a mission expected to last 4 years. It has now been operating for over 12 times that original mission length in an environment its designers never planned for, and it just handed us one of the most detailed pictures we have ever had of what lies immediately outside our solar system. That is not really a story about doom. It is a story about the extraordinary payoff of stubborn, patient, decades-long persistence, about engineers in the 1970s who happened to overbuild something durable enough to still be teaching us new things half a century later, and about the fact that some of the most important discoveries in the history of space exploration came not from a dramatic planned encounter, but from a graduate student quietly staring at a faint, strange line on a plot, refusing to dismiss it as noise and asking one more question. So, what did Voyager 1 actually confirm? Not a monster at the edge of the solar system, not some literal threat lurking in the dark. It confirmed that the boundary of our home is dynamic, pressured, and turbulent rather than calm and symmetric. It confirmed that the space between the stars has structure and motion on scales we can now measure, roughly the size of the distance between Earth and the Sun, rippling with density changes that likely trace back to forces as violent and as ancient as supernova explosions. It confirmed that our entire solar system is not simply floating through the galaxy in some quiet, protected pocket, but is instead actively colliding with and being reshaped by the material around it, a slow, permanent, ongoing collision that has been happening the entire time. Human civilization has existed on the small planet at the center of it, largely without our knowledge. And it confirmed, in the most human way possible, through a fixed, non-negotiable power budget, slowly ticking down toward zero, that even our most successful, most resilient piece of engineering has limits, and that the window for learning these things directly, rather than through models and inference, does not stay open forever. It helps to sit for a moment with just how strange the engineering side of this story really is, because the discovery itself only exists thanks to a chain of decisions made by people who could not have known in the 1970s what any of this would eventually mean. The team designing Voyager 1 had to build a spacecraft that could survive a 4-year mission through the harsh radiation belts of Jupiter, the extreme cold of deep space, and the total absence of any possibility of a repair visit ever, for any reason. Every part had to work the first time, every time, for the entire life of the mission, with no do-overs. That kind of engineering discipline tends to produce machines that are wildly overbuilt for their stated purpose, and Voyager 1 is a textbook example. The plasma wave instrument, along with a handful of other systems, was constructed to standards far exceeding what a 4-year planetary mission technically required, because nobody wanted to be the reason the spacecraft failed at Jupiter over a corner that got cut to save weight or money. Decades later, that same conservative, almost paranoid engineering culture is the entire reason there was still a working instrument out past 160 astronomical units capable of catching a signal nobody was expecting. It is worth comparing Voyager 1's situation to its twin, because the differences are almost as informative as the similarities. Voyager 2 took the longer road, flying past Jupiter, Saturn, Uranus, and Neptune, becoming the only spacecraft in history to visit all 4 giant planets. A feat that will likely stand for a very long time given how rare that particular planetary alignment is. Voyager 2 finally crossed its own heliopause boundary in November of 2018, 6 years after its sibling, at a slightly different location and angle relative to the Sun, giving scientists a second independent data point for what the edge of the heliosphere actually looks like from another direction. Crucially, Voyager 2's plasma instrument, the direct particle detector, still worked when it crossed over, unlike Voyager 1's, which had failed decades earlier. That gave researchers a rare chance to cross-check the indirect, oscillation-based density measurements coming from Voyager 1 against a genuine direct measurement from Voyager 2, and the 2 datasets lined up, which is part of why scientists trust the picture that has emerged. 2 spacecraft entering interstellar space from 2 different points, both describing a region shaped by pressure, structure, and turbulence rather than by empty, featureless calm. There's also a very human layer to this story that rarely makes it into the headlines, and it deserves attention because it explains why any of this discovery was even possible in the first place. The Voyager mission today is run by a small, dedicated team, a fraction of the size of the army of engineers who built and launched it in the 1970s. Many of the original blueprints exist only on paper. Some of the programming languages used to write the spacecraft's onboard software are so old that engineers occasionally have to track down retired colleagues, some in their 80s, to help interpret decisions made half a century ago. In 2023, a garbled, unreadable stream of data threatened to end the mission entirely, until engineers traced the problem to a single corrupted chip in the flight data system, and painstakingly rewrote the affected code to route around the failure, reviving the spacecraft's ability to communicate coherently after months of what looked like the beginning of the end. That kind of quiet, unglamorous persistence, a small team fighting to keep a decades-old machine alive far longer than anyone ever expected, is precisely what allowed the plasma wave instrument to still be listening when that strange, faint hum first appeared in the data. Every additional year of operation has been earned, not assumed. That persistence also reframes what confirms what we all feared really means here, because there is a second, subtler fear this story surfaces, one about scale rather than danger. For most of human history, the edge of what we could study was the edge of what we could see with our eyes. Then later, the edge of what our telescopes could resolve. Voyager 1 represents something categorically different. Not a better view from a distance, but an actual physical presence in the place being studied. A set of instruments sitting inside the environment itself, recording what it is actually like, rather than inferring it from light that traveled billions of kilometers to reach a lens on Earth. And what that physical presence reveals is a humbling kind of scale. 172 astronomical units sounds like an enormous distance, and by any human measure it is. But the interstellar medium researchers are now mapping the turbulence, the density gradients, the outer heliosheath where interstellar plasma flow gets compressed and decelerated by the heliosphere. That entire structure may not even level off until a spacecraft reaches something like 200 to 250 astronomical units, a distance Voyager 1, at its current speed, would need on the order of another 60 to 70 years to cover. decades after its instruments will have gone silent for good. We are getting a partial answer to a question that will not be fully answered for generations, if it ever is, using existing technology and existing missions. The picture Voyager 1 has handed us is not the whole picture. It is the first few pages of a much longer, much stranger book that nobody currently has a firm plan to keep reading. 46 hours for a message to make the round trip. 25.9 billion kilometers of distance. 48 years of continuous operation on a spacecraft with less computing power than a musical greeting card. A discovery made not by a dramatic flyby or stunning photograph, but by a faint, persistent hum almost nobody was even looking for, hiding in data that had been silently accumulating for years. That is the actual story here, and it is, in its own way, more remarkable than anything a more sensational headline could invent. We do not need to exaggerate what Voyager 1 found to understand why it matters. The real numbers, the real measurements, the real unglamorous, patient, decades-long grind of a spacecraft that refuses to stop talking to us, tell a story, dramatic enough on their own, that the edge of our world is not the quiet, empty boundary we assumed it was, that something vast and turbulent and ancient is pressing in against the bubble that shelters us, and that for a little while longer, we still have one small, aging, extraordinary machine out there listening to it and telling us what it hears.